What if everything you know about the universe, how it began, how it works, even what it's made of, is just the surface of something far stranger, far more mysterious? Picture this: the fabric of reality itself, woven not from solid matter but from probabilities, from particles that exist in multiple places at once until you look at them, from forces so bizarre they defy common sense. This isn't science fiction. This is the frontier of quantum origins, the mind-bending theories that suggest our universe might have emerged from a cosmic dance of uncertainty, a flicker in the vast unknown. And the deeper we dig, the more questions we uncover, questions that challenge everything we thought we knew about existence itself. Think about the last time you stared up at the night sky, feeling that mix of awe and wonder. That's the same spark that drives scientists to ask the biggest questions. Where did all this come from? How did nothing become something? For centuries, we've turned to myths, to religion, to classical physics for answers. But now, quantum theory is rewriting the story, proposing possibilities so radical they sound like magic. Imagine a universe where time isn't linear, where particles blink in and out of existence, where the very act of observation shapes reality. These aren't just abstract ideas, they're clues, pieces of a puzzle that might explain how everything, from the tiniest atom to the largest galaxy, came to be. So why does this matter to you? Because understanding the quantum origins of the universe isn't just about satisfying curiosity. It's about unraveling the very nature of reality. Every discovery peels back another layer, revealing a cosmos more interconnected, more mysterious, and more astonishing than we ever imagined. And today, we're diving into 30 of the most groundbreaking theories that attempt to explain how our universe emerged from the quantum void. From parallel worlds to cosmic holograms, from timeless beginnings to realities woven from pure information, these ideas will stretch your mind in ways you didn't think possible. Buckle up, because by the end of this journey, the universe might not look the same way again. The very beginning of everything might trace back to something almost unimaginably small, a tiny flicker of uncertainty in the void. That's the heart of the first theory. Our universe didn't emerge from nothingness, but from a quantum fluctuation in an otherwise empty but seething vacuum. Picture a calm ocean, perfectly still on the surface, yet beneath, it's teeming with invisible ripples, particles popping in and out of existence too quickly to notice. Now imagine that same restless energy, but on a cosmic scale. In the moments before the Big Bang, the vacuum of space wasn't truly empty. It crackled with zero-point energy, a kind of background hum left over when you remove everything else: matter, light, even heat. This energy isn't just theoretical. We've seen hints of it in lab experiments where particles seem to borrow energy from nowhere, vanishing as quickly as they appear. But in the early universe, one of these tiny fluctuations didn't just vanish. Instead, it ballooned outward, stretching space itself in an explosive moment we now call the Big Bang. What's even stranger is how those minuscule quantum ripples might have shaped the cosmos we see today. Those irregularities, tiny differences in density, became the seeds for galaxies, stars, and even the vast cosmic web that connects everything. Without them, the universe might have been perfectly smooth, lifeless, and dark. But here's the real twist. This means the entire universe could have started as a statistical blip, a random twist in the fabric of reality that somehow stuck. It's like rolling a dice an infinite number of times. Eventually, you'll land on the one outcome that changes everything. And if that's true, it raises another dizzying possibility. Our universe might not be the only one. If a quantum fluctuation created everything we know, could the same process have spawned countless other universes, each with its own laws of physics? The idea that we owe our existence to a cosmic roll of the quantum dice is both humbling and exhilarating, because it means the universe isn't just stranger than we imagined, but stranger than we can imagine. But what if our universe isn't the only one? What if it's just a single bubble in an endless cosmic foam, floating alongside countless others, each with its own version of reality? This is the multiverse hypothesis, a theory so vast it redefines the meaning of everything. At its core, this idea suggests that the same quantum fluctuations that may have sparked our Big Bang didn't just happen once. Instead, they could be happening endlessly, birthing new universes like bubbles in a boiling pot, each with its own unique set of physical laws. Think of it like this. Imagine a vast ocean where every wave that crests becomes its own self-contained world. Some waves are tiny, collapsing almost instantly. Others grow into sprawling, stable universes where matter clumps into galaxies and life might emerge. And just as no two waves are identical, no two universes would share the exact same rules. In one, gravity might be stronger, crushing stars into black holes almost immediately. In another, the forces that bind atoms could be so weak that matter never forms at all. Our universe, with its delicate balance of constants fine-tuned for life, might just be the rare exception in an infinite sea of failed experiments. The math behind this isn't just speculative, it's rooted in quantum mechanics and cosmic inflation theory. When our universe expanded violently in the first moments after the Big Bang, space itself stretched faster than light. But what if that inflation never truly stopped? What if it's still happening elsewhere, creating pocket universes disconnected from our own? Some theories even suggest these other realities could exist mere millimeters away from us, separated by dimensions we can't perceive. It's like living in one room of an endless mansion, unaware of the doors hidden in the walls. Here's where it gets even stranger. If the multiverse is real, there could be versions of you out there, countless variations shaped by every possible quantum decision. A universe where you took that job offer, one where you never existed, even one where the laws of physics allowed dragons to soar through the skies. And while that might sound like science fiction, it's a staggering possibility that emerges naturally from the equations. The multiverse isn't just about alternate histories, it's about alternate realities, each with its own fundamental truths. Yet for all its grandeur, this idea leaves us with a haunting question. If we're just one universe among infinite others, does that make our existence meaningless or more miraculous than ever? After all, in a sea of infinite possibilities, the fact that we ended up in a universe where life could arise at all might be the greatest cosmic lottery win of all time. What if the Big Bang wasn't the beginning, just a turning point in an endless cosmic cycle? Loop quantum gravity takes the idea of a singular origin and flips it on its head, proposing that our universe might be the rebound of a previous one, crushed to its limit before springing back in a dramatic cosmic bounce. Forget a fiery explosion from nothing. Picture instead a universe that breathes, expanding and contracting like a colossal lung, with each collapse giving birth to a new chapter of reality. This theory emerges from the strange world of quantum gravity, where the fabric of space isn't smooth and continuous but woven from tiny, indivisible threads like pixels on a screen. At the smallest scales, these threads twist and knot, creating a structure so dense that gravity itself becomes quantum, obeying rules far wilder than Einstein's relativity. When a dying universe contracts under its own weight, it doesn't just vanish into a singularity. Instead, the quantum nature of space-time resists total collapse like a spring compressed to its limit. The pressure becomes so immense that it triggers a rebound, a cosmic bounce flinging space outward in what we now call the Big Bang. Imagine throwing a rubber ball against the ground. The harder it hits, the higher it bounces back. Now replace the ball with an entire universe collapsing inward until quantum forces kick in, reversing the collapse into a new expansion. The remnants of the old universe, its matter, energy, even the echoes of its history could have been recycled into ours like a phoenix rising from its own ashes. Some models even suggest subtle fingerprints of the previous universe might linger in the cosmic microwave background, like scars from a life before the bounce. But here's where it gets even more fascinating. If this cycle repeats endlessly, stretching across eons we can't comprehend, then time itself might be circular, not linear. There's no true beginning or end, just an infinite dance of universes being born, dying, and being reborn. And if that's the case, the laws of physics might not be arbitrary rules but survivors, refined over countless cycles to allow complexity, and maybe even life, to emerge. Yet the big question remains, how do we test something so monumental? Loop quantum gravity makes predictions like subtle ripples in spacetime from the bounce itself that future telescopes might one day detect. Until then, the theory offers something just as valuable, a radical reimagining of our place in the cosmos. We might not be the first chapter in this story, just the latest verse in an epic poem written by the universe itself. The world around us feels solid, tangible, three dimensions of depth and distance we navigate every day. But what if that's just an illusion? Enter the holographic principle, a theory so radical it suggests our entire universe might be a projection, like a cosmic movie screen, with the real action happening on a distant two-dimensional surface. Imagine peeling back the layers of reality only to find that everything, every star, every planet, even your own thoughts, is just information painted onto the fabric of space-time at its most fundamental level. This idea didn't come from nowhere. It grew out of one of the most perplexing puzzles in physics, black holes. When matter falls into a black hole, it vanishes from our universe, seemingly erased. But quantum mechanics insists information can't be destroyed. It has to go somewhere. In the 1970s, physicist Jacob Bekenstein calculated that the entropy of a black hole, a measure of its hidden information, isn't scattered throughout its volume but proportional to its surface area. In other words, all the data about what fell in could be encoded on the event horizon, the black hole's outer boundary, like a celestial hard drive. Take a hologram, shine light on a flat, patterned surface, and suddenly a three-dimensional image appears. The holographic principle applies this logic to the universe itself. The math suggests that all the information needed to describe our three-dimensional reality could fit perfectly onto a two-dimensional boundary at the edge of space, no extra dimensions required. It's as if the universe is running on a cosmic projector, with every event, every particle collision, just a shadow play of deeper processes we can't see. But how could this possibly work? Think of a computer simulation where a vast open world is rendered from lines of code. The holographic universe might operate similarly, with the code written on a distant surface we'll never perceive. Even stranger, this could mean that time and space aren't fundamental, just emergent properties like the way temperature emerges from the motion of atoms. If true, it would rewrite our understanding of reality at the most basic level, turning the universe into the ultimate illusion. Yet the implications go even further. If the holographic principle holds, it could solve one of physics' biggest headaches, uniting quantum mechanics with gravity. By treating space-time as a projection of quantum information, the theory bridges the gap between the tiny world of particles and the vast scales of relativity. It's a bold vision, one where the universe isn't just stranger than we imagined, but stranger than the very language we use to describe it. So the next time you reach out to touch something, a book, a doorknob, the bark of a tree, ask yourself, are you really feeling solid matter or just the echo of data flickering from the edge of existence? The answer might redefine what it means to be real. Here's a bizarre thought. What if the universe actively chooses which quantum possibilities become real? Not through some mystical force, but through a process as ruthless as natural selection. This is the heart of quantum Darwinism, a theory that suggests the classical world we see isn't just random chance, but the result of quantum states battling for survival. Picture a quantum particle existing in multiple states at once, a blur of possibilities. But the moment you measure it, that blur collapses into a single, definite outcome. Why that outcome? Why not one of the countless others? The answer might lie in something called quantum decoherence. Imagine tossing a pebble into a still pond. At first, the ripples are clean, predictable, but as they spread, they bump into leaves, twigs, other ripples until the original pattern is lost in the chaos. Quantum systems work similarly. A particle starts in a pristine superposition, but the instant it interacts with its environment, a stray photon, a whiff of air, its delicate quantum state starts fraying. Over time, only the most stable states withstand this environmental noise, while the others fade away like echoes. These survivors are the ones we perceive, the fittest quantum states that get to shape reality as we know it. Think of it like a game of whispers. You start with a precise message, but as it passes from person to person, details get distorted until only the most robust parts remain. In quantum Darwinism, the universe is that game, and the message is the quantum information that survives long enough to be observed. The twist: this isn't passive. The environment isn't just erasing possibilities, it's selectively amplifying certain states, making them more likely to be detected. It's as if reality itself has a bias, favoring configurations that can withstand the onslaught of constant interaction. But here's where it gets mind-bending. If quantum Darwinism is correct, then the solid, predictable world we experience isn't fundamental. It's the end product of an invisible competition. The chair you're sitting on, the screen in front of you, even your own hands, are just the winners of a quantum tournament, states that outlasted the rest. This could explain why we never see Schrödinger's cat both alive and dead in real life. The environment selects one outcome long before we look, yet this raises a profound question: what determines which states are fittest? Some researchers suggest it's about redundancy. The states that get copied most widely into the environment are the ones we observe. Like a viral meme spreading across the internet, the quantum states that proliferate become the reality we share. Others propose it's about stability, with certain configurations resisting decoherence longer. Either way, the implication is staggering. Our perception of reality might be a collective hallucination, shaped by the quantum versions of natural selection. So next time you glance at the moon or touch a table, remember, you're not seeing the quantum soup beneath, you're seeing the survivors. What if the end of our universe isn't the end at all, just the quiet prelude to another beginning? Roger Penrose's conformal cyclic cosmology takes the idea of an eternal cosmos to a breathtaking extreme, proposing that universes don't just die and reboot, they transform, shedding their old skin in a quantum reset that erases time itself. Picture this: trillions of years from now, the last black holes evaporate into faint whispers of radiation. Matter itself decays into particles too feeble to interact, and the cosmos stretches into an infinite, featureless expanse. But instead of fading into nothingness, this silent, empty state becomes the birthplace of a new universe, reborn through a mathematical trick of geometry. At the heart of Penrose's vision is a radical rethinking of how time and space behave at cosmic scales. In the far future, when expansion has diluted everything to near nothing, the universe loses any meaningful sense of scale. Distances become irrelevant, temperatures uniform. In this state called conformal invariance, the cosmos has no clock, no yardstick, just pure, timeless geometry. And here's the twist: mathematically, this state looks identical to the ultra-hot, ultra-dense conditions of the Big Bang. Penrose argues that the end of one universe could seamlessly become the start of another, not through a violent collision or bounce, but through a quiet reconfiguration of spacetime itself. It's as if the universe hits a cosmic reset button, scrubbing away all traces of the past while preserving the underlying quantum fabric. But how does entropy, the relentless march toward disorder, fit into this cycle? Entropy is the reason time has a direction, why eggs don't unscramble themselves. Yet in Penrose's model, black holes act as cosmic vacuum cleaners, swallowing entropy and erasing it when they evaporate. By the time the universe reaches its conformal state, entropy is effectively zeroed out, leaving a blank slate for the next cycle. And here's the wildest part. Penrose and his collaborators claim to have found evidence of this process in the cosmic microwave background, ancient imprints of black hole collisions from a previous universe, lurking like echoes in the static of deep space. This isn't just poetic symmetry, it's a testable hypothesis. If concentric rings of temperature variation in the microwave background, patterns too precise to be random, can be confirmed as relics of pre-Big Bang events, it would rewrite our understanding of cosmic history. Imagine holding a photograph of the universe before ours, glimpses of an era when time ran backward, when black holes from a forgotten age collided and left their signatures in the sky. Yet the implications go deeper. If Penrose is right, then the arrow of time isn't an absolute rule, it's a local phenomenon reversing with each new cycle. The Big Bang wasn't a beginning but a transition, a moment where infinite future met infinite past. And if that's true, then every star, every planet, every life form that ever existed might be part of an endless cosmic loop, not just repeating but evolving, with each cycle subtly different from the last. So the next time you hear someone say, "Nothing lasts forever," remember, in Penrose's universe, nothing ever really ends. It just waits in the silent dark for its next turn to begin. John Wheeler, one of the great minds behind quantum theory, once asked a question that still haunts physics today. Does the universe exist without an observer to perceive it? His answer, the participatory universe, turns the traditional view of reality inside out. Instead of a fixed cosmos unfolding on its own, Wheeler suggested that consciousness itself might be the missing ingredient, the force that transforms quantum possibilities into concrete reality. Imagine a vast cosmic game of 20 questions where the universe doesn't truly take shape until something or someone asks the right questions. At the heart of this idea is the infamous double-slit experiment, where particles like electrons behave as waves until measured, then suddenly choose a definite state. Wheeler extended this strangeness to the cosmos, proposing that quantum fluctuations in the early universe only became real when observed by conscious beings us. It's as if the universe was waiting, a fog of probabilities, until life evolved to give it meaning. This isn't mysticism, it's a radical twist on quantum mechanics, where observation isn't passive but participatory, actively shaping the past as well as the present. Think of an old Polaroid photo developing. In Wheeler's view, the universe works similarly. Events only develop into reality when observed, even retroactively. He imagined a cosmic-scale version of the double-slit experiment, where light from distant quasars could be forced to decide its path billions of years ago based on measurements we make today. The implications are staggering. Our present observations could theoretically rewrite quantum history, as if the universe were editing its own script on the fly. But here's the catch. If consciousness plays this pivotal role, where does it begin? Does a single-celled organism count as an observer, or does it require complex thought? Some interpretations suggest even inanimate detectors can collapse quantum states, pushing back against Wheeler's idealism. Yet the core mystery remains: why does observation have any effect at all? Perhaps the answer lies in information. Wheeler famously coined the phrase "it from bit," proposing that every particle, every force, might ultimately be about information exchange, with consciousness as the ultimate processor. The participatory universe blurs the line between physics and philosophy, forcing us to confront a possibility even Einstein resisted: that reality might not be an external stage but a collaborative performance. And if that's true, then every glance at the stars, every measurement in a lab, isn't just uncovering the universe, it's completing it. string theory was supposed to be the theory of everything, a single framework uniting quantum mechanics and gravity under one elegant mathematical roof. But instead of simplicity, it gave us a cosmic hall of mirrors, 10 to the power of 500 possible configurations, each representing a universe with its own unique laws of physics. That's a 1 followed by 500 zeros, a number so vast it dwarfs the atoms in our observable universe, and buried somewhere in that unimaginable landscape, like a single grain of sand on an endless beach, lies our particular universe with its just right constants allowing stars, planets, and life. The unsettling implication: we might be living in a quantum fluke, a random draw from a cosmic lottery where almost every other ticket leads to a dead, broken, or unrecognizable reality. Picture a cosmic tuning machine with more knobs and dials than any engineer could count. Each twist adjusts a fundamental force or particle mass, the strength of gravity, the charge of an electron, even the number of spatial dimensions. In most settings, matter collapses instantly, atoms never form, or the universe tears itself apart in seconds. But through sheer statistical chance, a handful of combinations allow complexity to emerge. This is the string theory landscape, where the vacuum of space isn't empty but seething with potential, eternally settling into different low-energy states like bubbles in a vast quantum foam. Our universe isn't special, just improbably lucky. The math behind this is both beautiful and terrifying. String theory requires extra dimensions, tiny, curled-up shapes at every point in space. But these dimensions aren't all alike. Their exact geometry determines how strings vibrate, which in turn fixes the laws of physics. Some shapes produce strong nuclear forces, others make gravity dominant. With so many possible configurations, the right one for life seems vanishingly rare. Yet here's the twist: in an infinite landscape, even the most improbable outcomes must happen somewhere. It's like shuffling a deck of cards forever. Eventually, you'll get a perfect shuffle by sheer chance. This leads to a startling philosophical shift. For centuries, we assumed the universe's laws were inevitable, waiting to be discovered like buried treasure. But the landscape suggests they're more like climate local conditions in a much grander multiverse. Just as Earth's atmosphere allows liquid water while Venus broils and Mars freezes, our physics might just be the Goldilocks zone of a much wilder reality. Some theorists take this further. If consciousness only arises in certain universes, then of course we find ourselves in one that allows it, a cosmic version of survivorship bias. Yet the landscape isn't without controversy. Critics argue it's untestable, more metaphysics than physics. Without evidence for other universes, how do we know the landscape isn't just mathematical fiction? Supporters counter that signatures might lurk in gravitational waves or the cosmic microwave background, subtle fingerprints of collisions with other bubble universes. Until then, the landscape remains a breathtaking possibility, that our universe's elegance isn't by design but by accident, a fleeting harmony in an endless quantum symphony where most notes never find their tune. So the next time you marvel at the stability of matter or the precision of physical laws, remember, we might be cosmic outliers, a single working configuration in a machine built mostly for failure. And if that's true, it makes our existence not just miraculous, but statistically astonishing, like throwing a dart blindfolded and hitting the one bullseye in a galaxy of targets. Quantum entanglement is often described as spooky action at a distance, a phenomenon where two particles, no matter how far apart, instantly mirror each other's states. But what if this quantum weirdness wasn't just a microscopic curiosity? What if it was the invisible scaffolding that held the early universe together? This is the bold idea that entanglement might have stitched the cosmos into a unified whole, solving one of its oldest mysteries, the horizon problem. Picture the universe just after the Big Bang, a blazing, rapidly expanding fireball. Scientists have long puzzled over how regions of space now billions of light years apart could have nearly identical temperatures, even though light wouldn't have had enough time to travel between them and even things out. It's like walking into two separate kitchens on opposite sides of the planet and finding pots of water boiling at exactly the same temperature, despite no heat being exchanged between them. Classical physics can't explain this cosmic synchronization, but quantum entanglement just might. The theory goes like this: in the universe's first moments, particles weren't just closed together. They were deeply entangled, their fates interwoven in a vast, invisible web. As space expanded at breakneck speeds during inflation, these particles were pulled apart at rates faster than light could bridge. But their entanglement remained, a quantum thread tying them together across unimaginable distances. This connection could have allowed information about temperature and density to spread instantly, ensuring that far-flung regions of the universe shared the same conditions before they were forever separated by expansion. Think of it like a synchronized dance troupe separated by a sudden earthquake. Even as the stage splits apart, each dancer remains perfectly in sync because they learned the same choreography when they were close. Similarly, entanglement in the early universe might have pre-programmed distant regions to evolve in harmony, leaving the uniform cosmic microwave background we observe today as a ghostly imprint of that primordial connection. Yet entanglement as cosmic glue isn't just poetic, it's mathematically plausible. Some models suggest that the fabric of spacetime itself could emerge from quantum entanglement, like a 3D hologram projected from entangled quantum data. In this view, gravity and geometry aren't fundamental but side effects of deeper entanglement relationships. It's as if the universe isn't held together by invisible forces, but by an invisible network of quantum handshakes, agreements forged in the first moments of existence that still bind everything today. But here's the twist: if entanglement really did orchestrate the early universe's uniformity, it challenges our very notion of cause and effect. Normally, nothing can influence something else faster than light. Yet entanglement defies that rule. Particles coordinate instantly, as if the speed of light were just a suggestion. This doesn't break relativity. No usable information is actually transmitted, but it does suggest that the universe's deepest layers operate outside classical logic. The implications are staggering. If entanglement shaped the cosmos, then today's vast, seemingly disconnected galaxies might still be quantum neighbors in some hidden dimension. And if we could map those ancient entanglements, we might uncover a blueprint of the universe's birth, a quantum fossil hidden in the void. For now, the idea remains a tantalizing hypothesis, but experiments with quantum simulators and deeper scrutiny of cosmic microwave patterns could one day reveal whether the universe really is bound together by spooky threads older than time itself. What if our universe isn't the ultimate reality, just an advanced simulation running on some unfathomable quantum computer in a higher dimension? This isn't just sci-fi speculation. The simulated universe hypothesis suggests that every galaxy, every atom, even your very thoughts, might be lines of code in a cosmic program, with the fabric of reality rendered at the smallest possible scale, the Planck length. Think of it like a video game where the graphics are so flawless you can't tell they're pixels until you look closely enough to spot the seams. The roots of this idea stretch back to philosopher Nick Bostrom's provocative trilemma. If civilizations inevitably create simulations indistinguishable from reality, and if those simulations can spawn their own simulations, then statistically, the odds favor us living in one of the countless simulated layers rather than the original universe. But quantum physics adds a chilling twist. At the Planck scale, 10 to the power of -35 meters, space isn't smooth. It's grainy, like a digital image when you zoom in too far. Some theorists argue this granularity isn't a quirk of nature but evidence of a resolution limit, the universe's equivalent of pixelation. Then there are the glitches. High-energy cosmic rays occasionally behave in ways that defy known physics, as if the simulation's rendering engine struggles at extreme energies. Quantum indeterminacy, particles existing in superimposed states until measured, could be the universe's optimization trick, only calculating precise values when necessary to save processing power. Even déjà vu has been jokingly called a buffering delay, though the real evidence is far subtler. But here's where it gets even stranger. If we're in a simulation, the architects might have left Easter eggs, mathematical constants too perfect to be random, or anomalies in the cosmic microwave background resembling error correction codes. Some scientists have seriously proposed testing the hypothesis by looking for computational rounding errors in high-energy particle collisions or probing spacetime for recurring patterns that hint at underlying code. Of course, the simulation argument has its critics. If the universe is a program, who's running it? And what about their universe? Is that a simulation too, ad infinitum? Others counter that the hypothesis is unfalsifiable, a cosmic solipsism with no exit. But the most haunting question isn't whether we can prove it, it's what happens if we ever do. Would the simulators let us keep playing or hit delete? For now, the theory remains a mind-bending paradox, the ultimate conspiracy with no conspirators, a universe that might be both all there is and someone else's experiment. The universe might seem stable, solid, a predictable stage governed by unbreakable laws. But what if that stability is just an illusion, a temporary state that could shatter in an instant? This is the terrifying possibility behind vacuum decay, a quantum doomsday scenario where the very fabric of reality could rewrite itself without warning. At the heart of this theory lies the Higgs field, an invisible energy field that permeates all of space, giving particles their mass. Think of it like a cosmic syrup, slowing down particles as they move through it, except this syrup also determines the fundamental rules of physics. Right now, the Higgs field is in a false vacuum, a stable but not perfectly stable state, like a marble resting in a shallow dip on a hillside. It seems secure, but with enough energy, or a random quantum fluctuation, it could roll into a deeper valley, a true vacuum with entirely different properties. And here's where it gets apocalyptic. If this transition happened even in a tiny corner of space, it would create a bubble of new physics that expands at the speed of light, obliterating the old laws of the universe as it grows. Picture a droplet of ink spreading through water, but instead of color, it carries a new set of constants. Gravity might vanish, atoms dissolve, even time itself could warp unpredictably. The boundary of this bubble would be a wall of pure energy, advancing so fast you'd never see it coming. One moment, the universe is as it's always been. The next, everything you know, every galaxy, every thought, every law of nature, ceases to exist in its current form. The scariest part, this isn't science fiction. The math checks out. Quantum tunneling, where particles spontaneously overcome energy barriers, is a well-documented phenomenon. On a cosmic scale, it could nudge the Higgs field into that lower state, triggering a chain reaction. And because the change would propagate at light speed, there'd be no warning, no time to react. By the time astronomers noticed strange readings from a distant star, the bubble could already be here. But before you panic, consider this. If vacuum decay is possible, why hasn't it happened yet in 13.8 billion years? Some physicists argue our universe's longevity suggests the Higgs field is metastable, teetering on the edge, but unlikely to tip in any realistic time frame. Others counter that absence of evidence isn't evidence of absence. We might just be in the calm before a storm that takes 1 trillion years to arrive. Still, the implications haunt the edges of cosmology. If vacuum decay can happen, it might already have happened elsewhere, with bubbles of new physics colliding like soap suds in a sink. We wouldn't know. The signals could still be light years away. And if that's true, our universe might be living on borrowed time, a temporary configuration in a cosmic game of Russian roulette where the trigger could be pulled at any moment by anything from a stray high-energy particle to an experiment in a futuristic collider. So the next time you look up at the stars, remember, their constancy isn't guaranteed. Reality as we know it might be just one quantum hiccup away from vanishing into something utterly unrecognizable, a reminder that even the laws of physics aren't as eternal as they seem. Time might feel like the most unshakable constant in our lives, ticking forward without pause, dictating schedules, aging, even the expansion of the cosmos. But what if time isn't a fundamental feature of the universe at all? What if it's more like a cosmic mirage, an illusion woven from the deeper, stranger fabric of quantum mechanics? This is the daring idea behind the theory that time emerges not from some cosmic clockwork, but from the intricate dance of quantum correlations, an aftereffect of particles interacting in ways we've only begun to fathom. Imagine stepping into a movie theater where the film reel has been cut into individual frames and scattered across the room. On their own, each frame is just a frozen moment, no movement, no story. But when someone starts arranging them in a sequence, suddenly there's action, cause and effect, the illusion of time flowing. In this theory, the universe works similarly. At its most basic level, there are only quantum events, particles entangling, states fluctuating with no inherent timeline. But when these events correlate, when one quantum state depends on another, the appearance of sequence emerges. It's not that time doesn't exist, it's that time is what happens when the universe's building blocks compare notes. The math behind this is as elegant as it is bizarre. In quantum mechanics, particles can become entangled, their properties linked no matter how far apart they are. But entanglement isn't just a spatial phenomenon, it can stretch across what we perceive as time too. Some physicists argue that the order of events isn't fixed until interactions record them, like a cosmic game of telephone where the message isn't the point, the act of passing it is what creates time's arrow. This means the past, present, and future might not be as distinct as we think. A particle's state now could retroactively influence its state a moment ago, not through time travel, but because time itself is knitted from these quantum handshakes. Think of it like a symphony where the notes don't follow a conductor's beat. Instead, each instrument responds to the others, creating rhythm purely through interaction. There's no external metronome, just the relationships between sounds defining the music's flow. Similarly, without quantum correlations, the universe might be a static jumble of possibilities. Time emerges because particles listen to each other, building sequences from the chaos. This radical perspective could solve one of physics' biggest headaches, uniting quantum mechanics with general relativity. Einstein showed that time bends and warps near massive objects, but his theory treats it as a smooth, continuous fabric. Quantum mechanics, meanwhile, deals in jumps and probabilities with no clear role for time at the smallest scales. If time is emergent, not fundamental, it could bridge these worlds, revealing that space-time isn't the stage but the performance, a collective hallucination of particles in conversation. Yet the implications go even deeper. If time arises from quantum links, then the universe before the first correlations might have been timeless, a frozen quantum soup waiting to stir. Some models even suggest that black holes, where gravity crushes space-time to a singularity, could be places where time unravels, reverting to its rootless quantum state. And if that's true, then the flow of time we experience every day might be as fleeting as a ripple on a pond, a temporary pattern in something far more mysterious. So the next time you glance at a clock, consider this. The seconds ticking away might not be measuring some universal constant, but the hum of countless quantum conversations, whispering the illusion of time into existence. The real question isn't why time moves forward, it's why we're convinced it does at all. David Bohm saw the universe not as a collection of separate objects, but as an endless dance of hidden connections, a cosmic river flowing beneath the surface of reality. His theory of the implicate order dared to challenge quantum mechanics' most baffling rule, that particles exist as probabilities until observed. Bohm argued that what we perceive is just an unfolded projection of a deeper, more intricate reality, where every electron, every photon carries secret instructions, hidden variables that guide their behavior in ways we can't directly see. Imagine watching a whirlpool in a stream. On the surface, it seems like an isolated phenomenon, but its motion is dictated by invisible currents beneath, by the entire river's flow. To Bohm, particles are like those whirlpool surface manifestations of something far more profound. At the heart of this idea is what Bohm called the quantum potential, an invisible field that doesn't push or pull particles like gravity, but guides them, shaping their paths with perfect precision. Think of it like a cosmic GPS, where every particle in the universe is navigating via the same hidden map. When electrons interfere with themselves in the double-slit experiment, creating wave-like patterns, Bohm's theory suggests they're not behaving randomly, they're following this deeper order, their trajectories choreographed by the quantum potential in ways that look probabilistic from our limited viewpoint. What makes the implicate order so radical is how it handles entanglement. In standard quantum mechanics, entangled particles influence each other instantly across any distance, defying Einstein's speed of light limit. But Bohm's hidden variables offer a workaround. If every particle is connected through the implicate order, then their seemingly spooky coordination is just the surface ripple of a deeper, instantaneous link. It's as if two dancers on opposite sides of the world are mirroring each other perfectly, not because of magic, but because they're both listening to the same silent conductor. Bohm's universe isn't just interconnected, it's holographic. He believed that every part contains the whole, like a single drop of ocean water holding the blueprint of all currents and tides. In the implicate order, a single electron's hidden variables might encode information about the entire cosmos, folded into its quantum state like a fractal pattern. This could explain why quantum systems seem to know about their environment instantly, because on some level, they are their environment, just unfolded differently. Yet the implicate order isn't without its critics. Some argue that hidden variables add unnecessary complexity when quantum probabilities work just fine. Others point out that Bohm's theory requires a mysterious pilot wave guiding particles, a mechanism that feels more like philosophy than physics. But in recent years, experiments with oil droplets bouncing on vibrating surfaces, uncanny analogues to quantum behavior, have breathed new life into Bohm's ideas, showing that hidden variables can produce quantum-like effects in the macroscopic world. The true brilliance of Bohm's vision lies in its poetry. He didn't just want to explain quantum mechanics, he wanted to restore a sense of wholeness to a science that had become fragmented by uncertainty. In his universe, randomness is an illusion, a veil over a deeper harmony where everything from galaxies to atoms moves in perfect, unseen synchrony. Whether his hidden variables are real or just a beautiful metaphor, they remind us that reality might be far more layered and far more connected than we dare to imagine. Black holes have long been thought of as cosmic vacuums devouring matter, light, and even information itself, leaving behind nothing but mass, charge, and spin. But what if these gravitational monsters aren't the featureless pits they seem to be? What if, beneath their event horizons, black holes hold onto intricate quantum details like cosmic fingerprints, subtly encoding the history of everything they've ever consumed? This is the essence of the quantum hair theory, a revolutionary idea suggesting that black holes might preserve far more information than we ever imagined, and in doing so could hold clues to the universe's deepest origins. The term quantum hair plays off an old physics joke. Black holes were said to have no hair, meaning they were bald, simple, and identical aside from those three basic traits. But recent breakthroughs have turned that notion on its head. Theoretical work now shows that when matter falls into a black hole, it doesn't just vanish, it leaves behind faint, quantum-scale imprints on the black hole's gravitational field. These imprints aren't visible in the traditional sense, but they subtly alter how the black hole interacts with the universe around it, like invisible grooves on a vinyl record. Think of it this way: toss a book into a fire and the pages seem lost forever. But if you could somehow measure the smoke's exact composition, the ash's microscopic structure, you might reconstruct fragments of the text. Similarly, quantum hair suggests black holes don't erase information, they scramble it, encoding it in ways we're only beginning to decipher. Some models even propose that this quantum fuzz on a black hole's surface could preserve data about the particles that formed it, stretching back to the universe's earliest moments. This isn't just about solving the black hole information paradox, it's a potential window into cosmic history. If black holes retain quantum details of their creation, the oldest ones, primordial black holes forged in the Big Bang's chaos, could be time capsules carrying encoded hints about the universe's initial conditions. Picture archaeologists sifting through ancient ruins, except here the ruins are gravitational echoes, and the artifacts are quantum fluctuations frozen in space-time. The implications ripple outward. If black holes really do store quantum information, it could mean the fabric of reality itself has a kind of memory, a way of preserving data across billions of years. This might even tie into theories like holography, where the universe's entire history could be written on a boundary we can't yet see. For now, detecting quantum hair remains a formidable challenge, like trying to read a whisper from across a galaxy. But with gravitational wave detectors growing more sensitive and quantum computers offering new ways to simulate extreme physics, we might one day crack the code. So the next time you picture a black hole, don't just see a void. Imagine it instead as a cosmic librarian, silently cataloging the universe's secrets in a language we're only starting to understand, one quantum strand at a time. At the smallest scales imaginable, far smaller than atoms, even smaller than the quarks that make them up, the smooth fabric of spacetime might not be smooth at all. Instead, it could be a seething, frothing ocean of quantum bubbles, popping in and out of existence so quickly that the universe itself appears calm and continuous, like the shimmering surface of a lake hiding a storm of currents beneath. This is the theory of space-time foam, where the very foundations of reality dissolve into a chaotic quantum dance at the Planck scale. Imagine zooming in on the surface of a table until the wood's grains become vast canyons, then further until atoms look like planets. Keep going past protons and electrons until you reach distances so tiny that gravity itself starts acting erratically, where spacetime isn't a stable grid but a boiling soup of microscopic wormholes, virtual particles, and fleeting black holes. These quantum bubbles don't last long enough to measure directly. Some blink into existence for mere fractions of a second, but their collective turbulence could be the reason spacetime behaves the way it does on larger scales. The implications are staggering. If spacetime is foamy at its core, then the universe might not be a static stage but a dynamic, ever-changing medium, with tiny fluctuations capable of birthing entire realities. Some theories suggest that under extreme conditions like the crushing pressures near a singularity, these quantum bubbles could inflate into full-fledged universes, budding off from our own like bubbles in a glass of champagne. It's as if every black hole, every cosmic collision, might be spawning new universes in its wake, each with its own laws of physics encoded in the quantum froth that birthed it. This idea bridges two of physics' greatest mysteries, quantum mechanics and gravity. Einstein's general relativity paints spacetime as smooth and bendable, while quantum theory insists everything is discrete, pixelated at the smallest scales. Space-time foam could be the missing link, a place where gravity becomes quantum, where spacetime itself is built from discrete, fluctuating units. Think of it like pixels on a screen. From a distance, the image looks seamless, but up close, you see the individual dots. Detecting this foam might seem impossible after all. How do you measure something vanishingly small and unimaginably brief? But astronomers have tried. By studying the light from distant quasars, they've looked for telltale signs of spacetime's graininess. If high-energy photons traveled through a foamy universe, their journeys might be subtly altered, like hikers navigating rough terrain versus smooth pavement. So far, the evidence is inconclusive, but the search continues, with next-generation telescopes poised to probe even deeper. What's most mind-bending isn't just the idea of space-time as foam, it's the possibility that this quantum turbulence could be the engine of creation itself. If universes can bubble up from the void, then our cosmos might be just one of countless others, each born from a random fluctuation in the quantum sea. And if that's true, then the question isn't just where did we come from, it's what else is bubbling out there just beyond the edge of perception. The universe we see, vast, ancient, and seemingly infinite, might just be one tiny bubble floating in an endless cosmic foam, a single drop in a storm of expanding realities. This is the mind-bending premise of eternal inflation, a theory suggesting that the Big Bang wasn't a one-time event but a localized spark in a far grander process, one that never truly stops. At its core lies the inflaton field, a mysterious quantum force that drove the universe's explosive expansion in its earliest moments. But here's the twist: while inflation ended in our pocket of space, creating the stable cosmos we know, it might still be raging unchecked in regions beyond our horizon, birthing new universes like bubbles in a boiling pot. Picture a fireworks display frozen mid-explosion, with some sparks bursting into colorful blooms while others remain silent, waiting their turn. The inflaton field works similarly. Some areas relax into stable states, allowing galaxies and life to form, while others remain stretched taut, continuing to expand exponentially. Every quantum fluctuation in those still inflating regions could nucleate a new bubble universe, each with its own unique physics. Some might have stronger gravity, others weaker nuclear forces, and still others might flicker out of existence almost instantly. Our universe just happens to be one of the lucky ones, a bubble where the inflaton field settled into the right conditions for complexity to emerge. The math behind this is both elegant and unsettling. Inflation isn't just a one-shot expansion, it's a self-replicating process, endlessly spawning new regions of space-time. Think of it like a cosmic chain reaction, where each new bubble becomes the seed for countless others ad infinitum. And because these bubbles are continually pushed apart by the unstoppable inflation outside them, they'll never collide or interact, leaving each one isolated in its own pocket of reality. It's as if the universe is a vast, ever-growing quilt, with each patch stitched separately, forever unaware of the others. But how could something so abstract have real-world consequences? The answer lies in the cosmic microwave background, the afterglow of the Big Bang. If eternal inflation is correct, subtle anomalies in this radiation, slight temperature variations or unusual polarization patterns might bear fingerprints of collisions with other bubble universes in the distant past. It's a long shot, but not impossible, like finding driftwood on a beach hinting at a shipwreck just beyond the horizon. What's most staggering isn't just the scale of eternal inflation, but the philosophical shift it demands. If this theory holds, then the universe isn't a single, elegant equation but a chaotic, ever-branching fractal, with realms where time runs backward, dimensions curl differently, or the very concept of matter is unrecognizable. And if that's true, then the ancient question, why does our universe seem fine-tuned for life, gets a radical answer. We're not special, just statistically inevitable. In an infinite foam of universes, even the most improbable outcomes must arise somewhere. So the next time you look up at the night sky, remember, you might be gazing not at the cosmos, but at your local bubble, a fleeting island in an ocean of inflation that never ends. Take the fabric of reality, the smooth, continuous spacetime we move through every day, and shatter it into the tiniest possible pieces. Not dust, not atoms, but fundamental geometric fragments like shards of crystal broken down to their simplest shapes. This is the radical vision of causal dynamical triangulation, a theory that dares to rebuild the universe from the ground up, one quantum-sized triangle at a time. At its core, this idea suggests that space-time isn't inherently smooth. Instead, it's stitched together from countless microscopic building blocks, tiny, four-dimensional chunks called simplices. Picture a mosaic where each tile isn't a flat square but a hyperdimensional pyramid, with edges representing the flow of cause and effect. When you zoom out far enough, these jagged pieces blend together, creating the illusion of a seamless cosmos. But at the smallest scales, reality might be more like a cosmic Lego set, with each block obeying strict quantum rules about how it connects to its neighbors. What makes this approach so compelling is how it handles time. In most quantum gravity theories, time either disappears entirely or becomes a fuzzy, ill-defined concept. But causal dynamical triangulation keeps time front and center, insisting that every simplex must connect in a way that preserves causality. No time loops, no backward jumps, just an orderly progression from one moment to the next. It's as if the universe has an internal rulebook. Every block must fit together so that causes always come before effects, stitching a coherent history into the quantum foam. The magic happens when these simplices assemble en masse. Run computer simulations with enough of them, millions, billions, and something astonishing occurs. They spontaneously arrange themselves into a structure that looks like our four-dimensional universe, complete with the familiar arrows of time and dimensions we recognize. It's like watching a flock of birds form intricate patterns in flight. No central planner, just simple local rules giving rise to emergent complexity. Even more striking, this process can generate different phases of space-time, some crumpled and chaotic, others smooth and expansive, suggesting that our universe's large, orderly structure might just be one possible configuration in a vast landscape of quantum geometries. But here's where it gets mind-bending. If space-time is built from these quantum blocks, then the Big Bang might not have been a singular point, but a phase transition. A moment when the universe's building blocks suddenly shifted from one pattern to another, like ice melting into water. This could explain why we don't see evidence of a before the Big Bang. Not because there wasn't one, but because time itself was structured differently. A crumpled quantum regime where cause and effect as we know them didn't yet apply. Critics argue that this approach is too rigid, too reliant on artificial discretization of a universe that might be fundamentally continuous. Yet its defenders point to real successes like reproducing the observed dimensionality of spacetime without any prior assumptions as proof that sometimes to see the whole picture, you need to break it down to its smallest, sharpest pieces. So the next time you glance at a clock or feel the solid ground beneath your feet, consider this. The flow of time and the space you occupy might not be primordial truths, but collective illusions, emerging from a deeper quantum dance where every step, every connection is a tiny act of cosmic geometry. What if the universe isn't just aware of itself? What if awareness is the universe? This is the spine-tingling proposition of quantum consciousness cosmology, a theory that blurs the line between mind and matter, suggesting that the cosmos might not merely contain consciousness but be consciousness, woven from the same quantum fabric as stars and galaxies. At the heart of this idea lies a radical inversion of perspective. Instead of brains producing awareness through neural activity, consciousness could be a fundamental feature of reality, like gravity or electromagnetism, with our minds merely tapping into a deeper cosmic field of sentience. The roots of this theory stretch back to the baffling observer effect in quantum mechanics, the way particles seem to choose their state only when measured. Some researchers, like physicist Roger Penrose and anesthesiologist Stuart Hameroff, argue this isn't just random chance. They propose that consciousness arises from quantum vibrations in microtubules, tiny protein structures inside brain cells, acting like quantum antennas tuned to the universe's fundamental awareness. But scale this idea up and something even wilder emerges. If microtubules can harness quantum processes to generate consciousness, could the universe itself, with its vast quantum fields and entangled particles, be a kind of cosmic brain? Imagine the cosmos as a neural network with galaxies like neurons connected by filaments of dark matter. The universe's synaptic wiring, every quantum interaction from the spin of an electron to the collapse of a star becomes a flicker of cosmic thought. In this view, black holes aren't just gravitational pits but processing nodes, crunching information in ways we can't yet fathom. Even the Big Bang might not have been a purely physical event but a moment of cosmic awakening, the universe becoming aware of its own existence. Critics dismiss this as panpsychism dressed in quantum jargon, arguing there's no mechanism for how microscopic awareness scales up to cosmic self-reflection. Yet supporters counter that entanglement. The instantaneous link between particles across vast distances could provide the scaffolding for a unified field of consciousness. Think of it like a symphony. Individual notes, quantum events mean little alone, but together they create harmony, cosmic awareness. The universe doesn't think like a human, but it might possess a primordial form of sentience with life as its most articulate expression. The implications are dizzying. If consciousness is fundamental, then the search for extraterrestrial intelligence takes on new dimensions. We might find it not in radio signals, but in the quantum coherence of nebulas or the rhythmic pulsing of quasars. It also redefines mortality. If our minds are localized excitations of a universal field, death might be less an end and more a reintegration, like a wave returning to the ocean. Of course, this isn't testable yet. But if future experiments detect quantum coherence in biological systems or find patterns in cosmic background radiation resembling neural activity, we might edge closer to answering the oldest question of all: is the universe alive, and are we its way of knowing itself? Until then, the theory remains a hauntingly beautiful possibility that every star, every atom, and every thought might be notes in a cosmic melody, a universe singing itself into existence. Paul Dirac's equations predicted a universe far stranger than anyone expected, one where every particle we see might be just the tip of a vast, invisible quantum iceberg. In the late 1920s, his math revealed something unsettling. For every particle with positive energy, there should exist a twin with negative energy, like a shadow realm of matter hiding just beneath the surface of reality. To make sense of this, Dirac proposed an extraordinary idea that what we perceive as empty space isn't empty at all, but a churning, infinite ocean of these negative energy particles, a Dirac sea so dense and uniform that we simply don't notice it. Picture the universe as a calm lake at dawn, but beneath the glassy surface, the water teems with unseen life. This wasn't just abstraction. Dirac's sea explained the bizarre behavior of electrons, which seemed to wink out of existence when they dropped to lower energy states. His solution: they weren't vanishing, they were diving into the sea, filling the holes left by negative energy particles. Those holes, Dirac realized, would behave exactly like particles with opposite charge, leading to the prediction of antimatter, later confirmed with the discovery of the positron. But the implications went even further. If the Dirac sea is real, then the vacuum of space isn't passive, it's a quantum pressure cooker, constantly simmering with potential. Now imagine a storm rippling across that sea. Quantum fluctuations could momentarily lift a negative energy particle out of the depths, leaving behind a hole we perceive as a positron, while the elevated particle becomes an ordinary electron. This is the origin of virtual particles, fleeting pairs of matter and antimatter that pop in and out of existence, borrowing energy from the vacuum before annihilating and returning it. We've detected these virtual particles in lab experiments like the Casimir effect, where unseeable quantum ripples push metal plates together, proving the vacuum is anything but empty. But here's where it gets cosmic. Some theorists suggest the Big Bang itself might have been a cataclysmic wave in the Dirac sea, a quantum disturbance so violent it ejected countless particles from the depths, creating the matter-filled universe we know. It's as if reality began with a stone thrown into that infinite ocean, sending ripples that became galaxies. Even dark energy, the mysterious force accelerating cosmic expansion, could be linked to this sea's latent energy, a pressure emerging from the quantum foundations of spacetime itself. Yet the Dirac sea raises haunting questions. If it exists, is our universe just a temporary froth on a boundless quantum ocean? Could other disturbances have birthed alternate realities? And if antimatter is truly the absence of negative energy, what else might be lurking in those depths? Dirac's vision, once dismissed as poetic license, now feels like a key to unlocking the universe's deepest secrets, reminding us that nothing, not even emptiness, is ever truly what it seems. We've all heard the quantum riddle. A particle exists in multiple states until someone looks, at which point it chooses one. But what if that rule doesn't just apply to tiny particles in a lab? What if the entire universe played by the same rules, waiting for an observer to bring it into focus? This is the staggering proposition of the observer effect at cosmic scales, the idea that reality itself might have remained a haze of quantum possibilities until consciousness emerged to pin it down. Think of the universe's first moments not as a definitive explosion, but as a superposition of countless potential universes, each with different physical laws, different geometries, even different numbers of dimensions. In this view, the Big Bang wasn't a single event but a quantum probability wave, a cosmic Schrödinger's cat, both expanding and collapsing at once. Only when some form of observation occurred did the universe collapse into the version we recognize, with stable atoms, predictable gravity, and the delicate balance that allows life to exist. It's as if the cosmos was a jigsaw puzzle with infinite ways to fit together, and observation was the hand that placed the final piece. But who or what could have been the first observer? Here's where the theory splits into wild possibilities. Some argue it was the universe observing itself, a self-referential loop where quantum fluctuations generated primitive awareness, which in turn solidified those fluctuations into matter. Others suggest the first conscious beings, perhaps early life forms, or even future civilizations retroactively collapsed the universe's wave function through the sheer act of perception. Imagine a snake biting its own tail, the end of the story influencing the beginning. The math behind this isn't pure speculation. Quantum mechanics insists that observation changes systems, and cosmology shows the universe's constants are suspiciously fine-tuned for life. Coincidence or consequence? Some models even propose that the cosmic microwave background, the afterglow of the Big Bang, holds patterns that reflect ancient quantum observations, like echoes of a choice made billions of years ago. Yet the implications unsettle as much as they awe. If observation shapes reality, does the universe exist uncharted, in places no one has ever looked? Are there still quantum branches where gravity is stronger, where dark matter is visible, where our laws of physics never took hold? And if consciousness is the anchor that pins down reality, what happens when we're gone? The theory doesn't just blur the line between physics and philosophy, it erases it, leaving us with a universe that might not just contain mysteries but be one. In all the vast and chaotic sea of quantum possibilities, one idea stands out as particularly unsettling: the notion that instead of entire universes bubbling into existence, random fluctuations might occasionally conjure something far stranger, isolated, self-aware minds floating in the void. These are the so-called Boltzmann brains, hypothetical entities that arise purely by chance, complete with false memories and sensory experiences, convinced they're living in a real world when in fact they're just momentary flickers in an otherwise silent cosmos. Think of it like this: imagine shuffling a deck of cards for eternity. given enough time, the cards will eventually arrange themselves into perfect order, not because of any guiding hand, but simply through sheer probability. Now apply that logic to quantum fields. Even in an empty, cold universe with no stars or galaxies, random fluctuations could, over unfathomable timescales, spontaneously assemble a fully formed, conscious brain, complete with fabricated memories of a past that never happened. One moment there's nothing, the next a mind wakes up bewildered, remembering a life, a name, a world, only to dissolve back into the void an instant later. This bizarre scenario comes from a cosmic twist on thermodynamics. The original Boltzmann brain thought experiment was meant to challenge our understanding of entropy, the universe's inevitable slide toward disorder. If the cosmos lasts long enough, entropy says even the most unlikely events will eventually happen, including the spontaneous formation of complex structures like conscious minds. But quantum mechanics takes this further, suggesting that in a vacuum teeming with zero-point energy, these freak occurrences might not even require time to unfold. A Boltzmann brain could pop into existence purely from quantum randomness, like a cosmic glitch in the system. Here's the real kicker. If these disembodied minds do arise more easily than full-fledged universes, then statistically, you are far more likely to be one of them, a lone, temporary observer hallucinating reality, than an actual human in a stable, continuous universe. After all, why would nature bother constructing an entire cosmos when a single self-aware illusion is infinitely simpler? This argument has kept physicists and philosophers up at night because, if true, it undermines not just our sense of reality, but the very foundation of empirical science. How could you ever trust your observations if your mind itself might be a random accident? Some theories try to sidestep the problem. Eternal inflation, for instance, suggests that universes like ours sprout so frequently that Boltzmann brains become statistically negligible. Others argue that consciousness might require more than just random particle arrangements, perhaps a specific kind of quantum coherence that chance fluctuations can't replicate. But the unsettling possibility lingers. In an infinite or near-eternal cosmos, every conceivable configuration of matter, no matter how improbable, must arise eventually, including minds that think they're real, only to vanish without a trace. So the next time you feel the solid weight of a book in your hands or the warmth of sunlight on your skin, ask yourself, are these sensations anchors to a real world or just the fleeting dream of a brain that shouldn't exist? The answer might be the most profound mystery of all, one that blurs the line between existence and illusion, leaving us to wonder if even the act of questioning is just another quantum accident, here one moment and gone the next. The cosmos we know, with its swirling galaxies, glittering stars, and the vast emptiness between them, might not have been born from a single explosive event, but from a collision of entire realities. This is the startling premise of the ekpyrotic universe theory, where our entire existence stems from a cataclysmic meeting of two higher-dimensional worlds in a realm beyond ordinary space and time. Forget the Big Bang's fiery singularity picture, instead a cosmic car crash unfolding in the shadows of dimensions we can't perceive, a violent encounter that set the stage for everything we see today. At the heart of this idea are brains, short for membranes, not the biological kind, but theoretical constructs from string theory. These brains aren't just surfaces, they're entire universes floating in a higher dimensional space called the bulk. Imagine two sheets of paper suspended parallel to each other in a dark room. From our perspective, those sheets might seem flat and empty, but zoom in, and each sheet could contain whole galaxies, stars, and civilizations, unaware of each other's existence until they move. In the ekpyrotic scenario, our universe lives on one of these brains, and its birth came when another brain, drawn by unseen forces, smashed into ours with unimaginable energy. This collision wasn't like two planets crashing. It was a quantum-scale event vibrating through extra dimensions, transferring energy so intensely that it sparked the expansion we now call the Big Bang. The aftermath left ripples, not just in space, but in the very fabric of reality. Those ripples could explain the patterns we see in the cosmic microwave background, the faint afterglow of the universe's infancy. It's as if the universe's baby photos contain fingerprints from a parent we've never seen, a shadowy brain whose embrace set everything in motion. What makes this theory so compelling is how it sidesteps some of the Big Bang's biggest puzzles. Inflation, the idea that the universe expanded faster than light in its first moment, isn't needed here. Instead, the brain collision provides a natural way to create a smooth, uniform universe without requiring fine-tuned initial conditions. The energy of the crash does the work, stretching space-time evenly like dough being rolled flat. Even the mysterious dark energy accelerating cosmic expansion could be a lingering effect, a slow rebound from that primordial impact. But the implications stretch further. If the ekpyrotic model is right, then our universe might not be alone in the bulk. Other brain collisions could have birthed other universes, each with its own physics, its own history. Some might be long dead, their energy dissipated. Others could be on a collision course with ours, destined to meet again in an endless cycle of cosmic destruction and rebirth. This isn't just a one-time event, it's a potential rhythm of existence, a universe that breathes in epochs rather than moments. Critics argue that without direct evidence of extra dimensions or brain interactions, the theory remains speculative. Yet supporters point to subtle clues, anomalies in the cosmic microwave background that don't fit standard inflation models, or gravitational waves that might carry echoes of pre-Big Bang events. Future experiments like ultra-sensitive gravitational wave detectors could one day spot the tremors of that ancient clash, a whisper from the moment our universe was struck into being. So the next time you gaze at the night sky, consider this. The stars above might be more than remnants of a fiery beginning. They could be the aftermath of a collision between worlds we'll never see, a secret written into the cosmos in dimensions just beyond our reach. And if that's true, then the universe isn't just expanding, it's still carrying the scars of the impact that started it all. The cosmic microwave background, the faint glow left over from the Big Bang, is often called the universe's baby picture, a snapshot of its earliest moments. But what if that picture holds hidden imperfections, tiny cracks in the cosmic facade that betray a far stranger origin? Buried in the microwave static are anomalies, patterns, and asymmetries that defy standard explanations, subtle fingerprints pointing not just to a hot, dense beginning, but to a quantum one. These aren't mere measurement errors, they're cosmic irregularities so precise, so baffling, that some physicists suspect they're echoes of quantum processes woven into the fabric of space-time itself. Take the so-called axis of evil, a peculiar alignment of temperature fluctuations in the CMB that seem to point in a preferred direction, a cosmic cardinal direction that shouldn't exist. If the Big Bang was truly uniform, these fluctuations should be random, scattered like darts thrown blindfolded. Instead, they cluster along an invisible line, as if the early universe had a built-in asymmetry. One explanation: quantum entanglement on a cosmic scale, where distant regions of the infant cosmos weren't just linked but coordinated, like dancers in a performance too vast to comprehend. Imagine flipping a coin 1,000 times and getting heads every time it lands on a Tuesday. The odds defy logic unless the coin flips were never truly independent to begin with. Then there's the cold spot, a sprawling region in the CMB significantly cooler than its surroundings, stretching across hundreds of millions of light years. Standard inflation struggles to account for it, but quantum theories offer a wild possibility: a collision with another universe. In some multiverse models, bubbles of space-time can brush against one another during cosmic inflation, leaving bruises in the microwave background. It's like finding a frozen patch on a lake and realizing something massive must have broken the surface long ago. Even stranger, certain statistical quirks in the CMB's temperature distribution resemble patterns seen in quantum systems, hinting that the universe's first moments weren't governed by classical physics, but by probability waves that only later collapsed into the reality we recognize. But how could quantum effects imprint on something as vast as the CMB? Think of the early universe as a quantum field fluctuating wildly like foam on a stormy sea. As inflation stretched space-time, those microscopic quantum jitters were blown up to cosmic proportions, frozen into the fabric of the universe as density variations. Over billions of years, those variations grew into galaxies and voids, yet their quantum origins remain encoded in the microwave background, like a whisper passed through time. Some models even suggest these anomalies could be relics of a pre-Big Bang phase, remnants of a quantum gravity regime where space-time was still pixelated, still finding its footing. The hunt for these quantum fingerprints isn't just academic. Future telescopes like the European Space Agency's Euclid mission will map the CMB with unprecedented precision, searching for telltale signs of quantum gravity or extra dimensions. If they find them, it won't just confirm a theory, it'll rewrite our understanding of cosmic birth. The universe's first moments weren't just a fiery explosion, but a quantum storm, and the echoes of that storm might still be ringing in the silence between the stars. The universe operates with eerie precision. Galaxies spin, particles collide, and the laws of physics hold firm across billions of light years. But what if this stability isn't just a happy accident? What if space-time itself is running a continuous cosmic debugging program, subtly fixing its own glitches behind the scenes? This is the radical proposition that the universe might function like a quantum error-correcting code, a self-healing algorithm written into the fabric of reality at the smallest scales. At its core, error correction is how computers detect and fix mistakes, extra bits of data that act as safeguards against corruption. Quantum computers take this further, using entanglement to protect information even when individual qubits fail. Now imagine scaling that idea up to cosmic proportions. If space-time is fundamentally quantum, then every particle, every fluctuation, could be part of a vast redundancy system where information isn't stored in one place but smeared across entangled networks. Lose a piece here and the system reconstructs it from fragments elsewhere, like a cosmic game of hide and seek where the rules ensure nothing ever truly disappears. The evidence for this isn't just speculative. Black holes posed a paradox. When matter falls in, its information seems lost forever, violating quantum mechanics' insistence that information can't be destroyed. But if space-time employs error correction, the data isn't gone, just scrambled and distributed across the event horizon's quantum threads. Think of it like a shattered vase whose pieces are scattered in a pattern that, if you know the code, allows you to reassemble it perfectly. This could explain how black holes radiate Hawking radiation while preserving information, like a corrupted file slowly being repaired as it's deleted. The implications ripple outward. If the universe is running error correction, it might explain why empty space isn't a chaotic quantum froth but a stable, predictable medium. Random fluctuations, virtual particles popping in and out of existence, could be the system's way of testing its own integrity, like a computer periodically checking for corrupted memory. Even the speed of light might not be a fundamental limit, but a side effect of how quickly quantum information can propagate reliably through the cosmic code. But here's the real twist. This theory suggests space-time isn't the foundation of reality, but a layer built atop something deeper, a quantum information network where geometry emerges from data relationships. It's as if the universe we see is the user interface, while the real action happens in lines of quantum code we're only beginning to decipher. future experiments with quantum gravity or simulations of holographic models could reveal whether space-time really is the universe's way of keeping its own secrets safe, a cosmic backup drive written in the language of entanglement. So the next time you marvel at the night sky's order, remember, the stars might not just be burning gas, but flawless lines in a cosmic program running error checks since the dawn of time. And if that's true, then the universe isn't just vast, it's virtually uncrashable. Every particle we know, electrons, quarks, even the elusive Higgs boson, might have a hidden twin, a mirror image partner lurking just beyond our current reach. This is the tantalizing promise of supersymmetry, a theory so elegant it could solve multiple cosmic puzzles in one stroke. Imagine a universe where every known particle has a heavier, undiscovered counterpart, electrons paired with selectrons, quarks with squarks, photons with photinos, each balancing the quantum scales in ways that explain why reality doesn't tear itself apart at the seams. At its core, supersymmetry is about symmetry, not the kind you see in a butterfly's wings, but a deeper, mathematical harmony woven into the laws of physics. The standard model of particle physics, while incredibly successful, has gaps wide enough to drive a quantum truck through. Gravity refuses to play nice with quantum forces, dark matter remains invisible, and the Higgs boson's mass seems unnaturally fine-tuned. Supersymmetry smooths these rough edges by introducing a new class of particles that act as cosmic counterweights. For every particle with integer spin bosons, there's a half-integer spin partner, fermions, and vice versa. This pairing doesn't just tidy up the math, it could stabilize the very fabric of reality. Take the Higgs boson. Its mass is precariously balanced, like a pencil standing on its tip. Quantum fluctuations should send it skyrocketing to energies far beyond what we observe, yet somehow it stays put. Supersymmetry's hidden particles provide a solution. Their interactions cancel out these runaway fluctuations with perfect precision, like two dancers moving in perfect opposition. It's as if the universe has a built-in failsafe, a quantum safety net we never knew was there. But supersymmetry's reach extends further. One of its lightest predicted particles, the neutralino, fits the profile of dark matter almost too well. Unlike the shadowy, unknown substance we've been chasing, neutralinos would be stable, electrically neutral, and abundant enough to explain the invisible scaffolding of galaxies. Picture the Milky Way not just as a swirl of stars, but as a halo of these elusive superparticles, their collective gravity holding everything together. Yet the theory isn't without its skeptics. Despite decades of searching, colliders like the Large Hadron Collider have yet to slam protons together with enough energy to produce these hypothetical twins. Some argue that if superparticles exist, they must be far heavier than initially hoped, hiding in energy regimes we can't yet access. Others propose that supersymmetry might be broken in ways that make its particles nearly undetectable, leaving only faint traces in cosmic rays or primordial gravitational waves. The stakes couldn't be higher. If supersymmetry is real, it would rewrite our understanding of quantum forces, dark matter, and even the universe's ultimate fate. If it's not, physicists face a crossroads: either embrace an even wilder explanation or admit that nature's deepest symmetries might be more subtle than we ever imagined. For now, the hunt continues, with every high-energy collision and deep space observation bringing us closer to answering a question that cuts to the heart of reality itself. Is the universe listening to a hidden harmony one only supersymmetry can hear? Time might be the most fundamental aspect of our daily experience, yet when we zoom out to cosmic scales or down to quantum depths, this familiar arrow starts to dissolve like mist in sunlight. At the heart of quantum cosmology lies a paradox so profound it shakes physics to its core. How can we speak meaningfully about time before the universe existed? After all, time as we know it emerged with the Big Bang, so what does before even mean when there's no space-time to measure it? Einstein's relativity treats time as a dimension woven into the fabric of the cosmos, malleable but real. Quantum mechanics, meanwhile, describes a world where particles exist in timeless superpositions until observed. When these two frameworks collide in quantum gravity theories, like string theory or loop quantum gravity, time becomes a ghostly variable, slipping through the equations like smoke through fingers. Some approaches eliminate time entirely, reducing it to an illusion emerging from quantum correlations. Others suggest time might be granular, a series of discrete quantum ticks at the Planck scale, where the smooth continuum we perceive shatters into something more like a cosmic flipbook. Take the Wheeler-DeWitt equation, a cornerstone of quantum gravity. This mathematical framework for describing the universe's wave function famously contains no time variable at all, as if the deepest layer of reality exists in a perpetual now. It's like trying to describe a movie by studying a single frame. The richness of narrative, cause and effect simply isn't there. Some physicists interpret this timelessness literally. The universe doesn't evolve through time but exists all at once, with our perception of flow just a stubborn cognitive illusion. But here's where it gets even stranger. If time isn't fundamental, how did it emerge? One provocative answer lies in quantum entanglement. Recent work suggests that time's arrow might arise from the way particles become increasingly entangled with their environment, a process called quantum decoherence. Imagine two dice thrown onto a table. Initially, their states are independent, but as they bounce and interact, their outcomes become correlated. Scale this up to cosmic proportions, and you have a universe where quantum links between particles create the appearance of a timeline, like threads weaving the fabric of causality itself. Yet this leaves the pre-Big Bang era in a conceptual limbo. Without space-time, without matter, how could anything happen? Some theories propose that quantum fluctuations in a timeless void could spontaneously generate temporal structure, like bubbles forming in boiling water. Others suggest time might be cyclic, with each universe's birth resetting the cosmic clock. The most radical idea, that time is fundamentally relational, existing only as a measure of change between objects. No stars, no particles, no change, no time. These aren't just abstract musings. If time is emergent rather than fundamental, it reshapes our understanding of black holes where time seemingly stops, and the universe's ultimate fate where entropy might render time meaningless. Future experiments probing quantum gravity or primordial gravitational waves could reveal whether time is woven into reality's foundation, or whether, like a desert mirage, it's something we've collectively imagined into being all along. Wormholes aren't just science fiction shortcuts through space. They might have been the universe's very first architects, stitching together the fabric of reality from threads borrowed from other dimensions. Picture this: in the seething chaos of the early cosmos, microscopic tunnels briefly pierced the void, funneling energy from some distant corner of the multiverse into our fledgling reality. These quantum wormholes wouldn't have been the gaping portals of Hollywood lore, but fleeting, subatomic fractures like bubbles forming in a pot of boiling water, vanishing almost as quickly as they appeared. Yet in their brief existence, they could have done something extraordinary, seeded the universe with the energy needed to ignite the Big Bang itself. This idea flips the traditional origin story on its head. Instead of a singularity bursting from nothing, imagine a cosmic relay race where energy slips through hidden tunnels from an older, dying universe into ours. The math behind this is as elegant as it is audacious. Wormholes, as Einstein's equations suggest, are theoretically possible bridges connecting distant points in spacetime. But in the extreme conditions of the quantum realm, these bridges could have formed spontaneously, acting as conduits for vacuum energy or even entire quantum fields. Think of it like a lightning strike between clouds. The wormhole is the jagged path that equalizes the energy difference between two realms, leaving behind a newborn universe crackling with potential. What's even wilder is how these wormholes could explain one of cosmology's biggest puzzles: why the universe started with such perfectly balanced conditions. The energy funneled through these tunnels wouldn't have been random. It might have carried imprints of the parent universe's physical laws, fine-tuned over eons. It's as if our cosmos inherited a cosmic recipe book with instructions on how to stabilize matter, calibrate gravity, and avoid collapsing into chaos. Some models even suggest that the universe's expansion rate, dark energy's mysterious push, could be a residue of this primordial energy transfer, like an echo of the wormhole's final pulse. But here's the twist: if wormholes seeded our universe, they might still be out there, not as tunnels, but as relics. Quantum gravity theories predict that these structures could have collapsed into ultra-dense, exotic matter, forming the seeds for today's black holes or even dark matter. Imagine the Milky Way's invisible halo not as a cloud of unknown particles, but as the fossilized remnants of the very conduits that birthed reality. Future gravitational wave detectors or quantum simulations might one day spot the faint tremors of these ancient structures, like archaeologists uncovering the foundations of a long-lost civilization. Yet the most profound implication isn't just about origins, it's about connection. If wormholes linked us to another universe once, could they still? The answer might lie in the quantum foam, where space-time is never truly still. Even now, microscopic wormholes could be flickering in and out of existence, whispering hints of a multiverse we'll never see. And if that's true, then the Big Bang wasn't an isolated event, just one note in an endless symphony of cosmic rebirth, where every universe is a branch on a tree whose roots reach deeper than time itself. What if the grand sum of everything, all matter, all energy, every swirling galaxy and flickering quantum particle adds up to precisely nothing? This is the startling claim of the zero universe hypothesis, a theory that turns existence itself into the ultimate cosmic balancing act. At its core lies a mind-bending equation. The positive energy bound up in stars, planets, and dark matter is perfectly cancelled out by the negative energy woven into gravity and the vacuum of space itself. The universe, in this view, isn't a thing that exists so much as a ripple in nothingness, a fleeting symmetry that somehow forgot to annihilate itself. Think of it like a cosmic ledger where every debit has a matching credit. Matter and light fill one column with their vibrant energy, while gravity, the curvature of space-time, piles up an equal debt in the other. Even the vacuum, that seemingly empty void, hums with negative pressure, a kind of quantum mortgage on reality. The math behind this is eerily precise. Einstein's equations show that a closed universe, one without edges or external boundaries, must have zero net energy. It's as if the cosmos is the ultimate free lunch, borrowing energy from itself in a loop so perfect it never needs repayment. Here's where it gets even stranger. If the universe truly balances to zero, then it could have emerged from pure quantum fluctuation, no divine spark, no exotic physics, just the same random jitter that creates virtual particles in a lab. In a vacuum teeming with zero-point energy, a tiny blip of positive energy might have spontaneously formed, paired with an equal negative counterpart, creating a self-contained bubble of reality that somehow stabilized. Picture a soap film momentarily bulging outward before snapping back, except in this case, the film is the void and the bubble became everything we know. But how could something as vast and complex as our universe arise from nothing? The answer lies in scale. At the quantum level, particles pop in and out of existence all the time, their brief lives funded by borrowed energy. The zero universe hypothesis suggests the Big Bang was just a larger, luckier version of this process, a fluctuation that, instead of vanishing, found a way to persist by balancing its books perfectly. Inflation, the universe's explosive early growth, might have been the mechanism that locked this balance in place, stretching the initial quantum wobble into a self-sustaining system. Critics argue that this doesn't explain why such a fluctuation would lead to a universe with structure, life, or consciousness. Yet supporters counter that in an infinite quantum sea, every possible fluctuation must occur eventually, including one that accidentally builds a cosmos hospitable to observers like us. It's the ultimate anthropic twist. The reason we see a universe with galaxies and atoms isn't because they're likely, but because they're necessary for us to be here asking the question. The implications are dizzying. If the zero-universe hypothesis holds, then existence itself might be the rarest of quantum accidents, a temporary asymmetry in a void that prefers perfect silence. And if that's true, then the ultimate fate of the cosmos, whether it expands forever or collapses back into nothing, might just be the universe remembering its original balance, settling its debts at last. So the next time you feel the weight of a book in your hands or the warmth of sunlight on your skin, consider this. You might not be holding anything at all, just the echo of a zero-sum quantum wink that hasn't yet blinked out. The universe isn't something that is, it's something that owes, and one day the bill might come due. Evolution might not just shape life, it could shape reality itself. Quantum Darwinism takes the eerie unpredictability of the quantum world and asks a revolutionary question. What if the stable universe we see isn't random, but the result of a cosmic survival of the fittest, where only the most robust quantum states persist across eons? At the quantum level, particles exist in a haze of possibilities. An electron isn't here or there until measured, spinning in a blur of potential positions. Yet somehow, when we look around, the world seems solid, predictable. Why? Because unstable quantum states vanish almost instantly, like soap bubbles popping in the wind, while durable configurations stick around long enough to build atoms, molecules, and ultimately us. This idea flips traditional quantum mechanics on its head. Instead of observation collapsing reality into a single state, quantum Darwinism suggests the environment acts as a kind of cosmic filter, amplifying certain quantum states while suppressing others. Imagine tossing a handful of sand into a river. Most grains wash away instantly, but a few catch in crevices, enduring the current. Over time, only those resilient grains remain visible. In the quantum realm, interactions with photons, air molecules, or even stray cosmic rays serve as the river, selecting states that can withstand constant bombardment. These survivors become the classical world we perceive, not because they're the only possibilities, but because they're the ones that didn't get erased by the universe's relentless noise. But here's where it merges with natural selection in a jaw-dropping way. Just as biological evolution favors traits that enhance survival, quantum evolution might favor states that maximize stability. Some theorists propose this isn't limited to tiny particles. Entire universes in a multiverse could undergo a similar pruning process. Universes where quantum fluctuations yield unstable physics, say, gravity that fluctuates wildly or matter that decays too quickly, would vanish almost instantly like cosmic stillbirth. Only those with the right fit of constants and laws would endure long enough to spawn galaxies, stars, and observers. It's as if the cosmos itself is subject to a grander version of survival bias, where we only find ourselves in a universe that worked because the others didn't make it. Evidence for this might already exist in the fine-tuning problem, the eerie precision of physical constants that allow complexity to arise. Why is gravity just strong enough to hold galaxies together but weak enough to let stars burn for billions of years? Why do protons and electrons balance so perfectly? Quantum Darwinism offers a spine-tingling answer. These aren't accidents, but the end result of an unthinkably long selection process where unstable configurations were filtered out like failed experiments. Even the arrow of time, the relentless march from order to disorder, could reflect this cosmic winnowing, with entropy acting as the ultimate fitness test. Yet the theory isn't without its skeptics. Critics argue it risks being a tautology. Of course, we observe stable states. They're the only ones that last long enough to be observed. Others question how quantum fitness could operate without some form of replication, a mechanism absent in non-living systems. Still, experiments with quantum systems in noisy environments show certain states do emerge as preferred, resisting decoherence far longer than others, a tantalizing hint that nature might indeed be playing favorites at the quantum level. The implications are staggering. If true, quantum Darwinism doesn't just explain why the universe seems so orderly. It suggests that beneath the surface, reality is a battlefield where only the most resilient quantum configurations get to shape the world we know. And if that's the case, then the atoms in your body, the light from your screen, even the force keeping your feet on the ground, might all be victors in a silent war that's been raging since the dawn of time. A war where stability is the ultimate prize and existence itself is the last observer standing. Imagine a universe still in its infancy, not yet filled with stars or galaxies, not even with distinct particles, but a swirling quantum fog where every possibility exists at once. This primordial haze wasn't just hot and dense, it was fundamentally undefined, a cosmic superposition where the very laws of physics hadn't yet chosen their form. And here lies the most unsettling question of all. Did this newborn universe need someone or something to look at it before reality could snap into focus? This isn't just philosophy, it's the quantum measurement problem scaled up to cosmic proportions, probing whether the universe's first moments required an observer to collapse its infinite possibilities into the orderly cosmos we know today. At the quantum scale, particles exist in a ghostly state of multiple possibilities until measured. An electron isn't here or there. It's both everywhere, a probability wave waiting to be pinned down by observation. Now take that uncertainty and stretch it across the entire early universe. Before atoms, before light, even before time as we understand it, every physical constant, the strength of gravity, the mass of electrons, the very dimensionality of space, might have existed in a similar haze of maybes. Inflation, the universe's explosive growth spurt, could have been less a deterministic process and more a quantum dice roll, one that only settled into our particular set of laws because some primordial measurement locked it in place. But who or what could have been the observer when no stars, no planets, no conscious beings yet existed? The answer might lie in the universe observing itself. Quantum decoherence, the process by which quantum systems lose their ambiguity through interaction with their environment, could have acted as a kind of cosmic measurement. Picture the early universe as a hall of mirrors, where every quantum fluctuation reflected off others, amplifying some states while cancelling out the rest. Over time, only the most stable configuration survived, like a chorus of voices where only the loudest harmony persists. In this view, the Big Bang's afterglow, the cosmic microwave background, isn't just a relic of heat. It's the universe's first self-portrait, a snapshot of the moment quantum potential crystallized into classical reality. Yet the implications go deeper. If the early universe needed decoherence to define its rules, it raises a staggering possibility. Other regions of spacetime might have measured themselves differently, leading to alternate physics. Beyond our cosmic horizon, there could be domains where gravity repels, where time runs backward, or where matter never clumped into galaxies. These aren't just parallel universes, they're fragments of a reality that never fully committed to being one thing or another, like a quantum experiment left eternally unresolved. The most radical interpretation, consciousness itself, might be woven into the fabric of cosmology. If reality requires observation to take shape, then the emergence of life isn't just a happy accident, it's the universe's way of completing itself. From this perspective, the first sentient beings to gaze at the stars weren't just products of cosmic evolution. They were participants, finalizing a story that began billions of years earlier in a sea of quantum uncertainty. It's as if the cosmos was a riddle waiting to be asked, a puzzle that only makes sense when there's someone there to solve it. Whether the universe needed a witness or simply tangled itself into stability, the mystery remains. Why this particular set of laws, this particular reality? The answer might be written in the oldest light we can see, or it might be staring back at us every time we look in the mirror. From cosmic holograms to quantum bubbles, from self-aware universes to hidden dimensions, we've ventured through a labyrinth of theories so radical they blur the line between science and metaphysics. Each one redefines not just how the universe began, but what it fundamentally is. Some paint reality as a cosmic fluke, others as an inevitable outcome of quantum logic. Some suggest we're living in a simulation, while others argue the universe itself is a conscious entity. The sheer diversity of these ideas isn't just a testament to human creativity, it's a reminder that the cosmos refuses to be boxed into a single origin story. What's astonishing isn't just how far these theories stretch our imagination, but how seriously they're taken by the scientific community. These aren't wild guesses, they're rigorous attempts to reconcile quantum weirdness with cosmic-scale mysteries, backed by equations that, against all intuition, work. Take loop quantum gravity's bouncing universes or the holographic principle's pixelated reality. These ideas emerged not from daydreams, but from the hard math of general relativity and quantum field theory. Even the most outlandish proposals like Boltzmann brains or vacuum decay are stress-tested against known physics, pushing the boundaries of what's plausible. That's the beauty of modern cosmology. It's a playground where the rules are strict, but the possibilities are infinite. Yet for all their sophistication, these theories share one humbling truth: we may never know which, if any, are correct. The quantum origins of the universe might be locked behind an impenetrable veil, a first moment too alien, too distant, or too entangled with the act of observation itself to ever fully unravel. But that's not a failure, it's an invitation. Every unanswered question is a catalyst for new ideas, new experiments, and new ways of seeing reality. Maybe the answer lies in gravitational waves whispering from the early universe, or in quantum computers simulating alternate physics, or in some yet undreamed tool that'll rewrite the rules entirely. So here's where you come in. Which of these theories resonates with you? Is our universe a hologram, a simulation, or one note in an eternal symphony of cosmic rebirth? Or do you have a wild idea of your own, something even the theorists haven't dared to propose? Drop it in the comments below, and let's keep the conversation as boundless as the cosmos itself. And if you're hungry for more mind-bending mysteries, from the enigma of dark matter to the paradoxes of time travel, hit that subscribe button and join us as we keep unraveling the universe one quantum thread at a time. The journey's just beginning.